Okay, so hello everybody. Hopefully I was able to successfully pull everyone from Nancy's talk into this session. So what we're going to try to do with these panel discussion sessions, and again, we have another one tomorrow, is use this as a time for the many trainees that we have here to ask some of the questions of both our speakers and the various the speakers, other people who might be here, in the audience, the organizers, any questions that might be on your mind, whether it's about specific research, whether it's about questions about finding jobs, getting more involved in computational neuroscience, creating collaborations, all of these challenges that we face as computational neuroscientists. This is the time for us to have these discussions. So again, if you have a question, please put that in the Ask a Question tab. I'll be monitoring that. If there's someone specifically you'd like to ask it to, any of the speakers that we've already had this morning, I believe they're all still here. Anyone who is on the organizing committee, anything like that, please feel free to sort of say specifically who would you like to ask that question. So I am going to invite Nancy back on screen right now. I'm going to invite Francis up on screen as well. Hello, Nancy.
Hello.
And hopefully Francis should be joining us momentarily.
Hi, Nancy.
Hi, Francis. I enjoyed your talk.
Thank you. Ditto.
So I figured I would get this started off by, one of the biggest questions that people asked in their sort of registration they wanted to hear more about was how people who are, very established in computational neuroscientists like the two of you, how you found this field and sort of, in made your mark in it. So I guess, maybe we'll start with Nancy. Could you sort of give us maybe a quick history lesson of how you found yourself in the computational neuroscience world?
I'd be happy to. I'd be also happy if you could help me eliminate where I am.
So do you still see your slides?
No, I don't see my slides. I see Nancy Kopel with an eye on it and followers. Can I get rid of that?
Yeah, so that should go away if you just move your mouse.
It doesn't.
But do you see myself and Francis?
Leave site. Do I leave site?
No. So we get Nancy. I think we might have just lost Nancy. So Francis, how about we start with you? Could you give us a little bit of a quick history lesson, sort of how you found yourself in computational neuroscience?
Yeah, well, I guess, part of the thing is how does one define the field of computational neuroscience, right? And not everybody would define it the same way. I mean, I think the main thing is it's an interdisciplinary field, as you know very well. And it's really using sort of the mathematical and computational tools to understand how the brain works. So, I mean, we're all sort of neuroscientists. And so the question is, how do you kind of get into the field, or how did I find myself in the field? Sorry, which one is it?
Yeah, so just sort of what your journey was, because it's such an ill-defined interdisciplinary field, I think some people, feel some anxieties about how do I find the postdoc, how do I find the faculty position in something that's so interdisciplinary. And this is great. So Nancy's back up on screen. So Francis, why don't you sort of walk us through, and then we'll go to Nancy next.
So I guess, yeah, I mean, Nancy has way more experience than me, of course. And I guess in terms of interdisciplinary, because in my case, it's always been loving math and loving biology and sort of how to combine it. And I sort of just kind of tried to find my way and identify people and areas that were trying to bringing it together, which is why I ended up in Boston with Eve, and then very fortunately was able to interact with Nancy and all the rest of it. So I think what you do is you seek out those situations where people are kind of doing that combination already. And in my case, I wouldn't say computational neuroscience was an established field as it sort of seems to be now. And so it's very diverse. And so I think yeah, I'm kind of going all over the place. But in my case, it's just sort of looking for those opportunities where people seem to be doing the combination. And then when you have that seed, people come. So I was very fortunate with Eve, and Larry Abbott was there at the time. And then Nancy started. So it just kind of becomes like a osmosis effect. Now there are sort of established groupings. So you're sort of more looking for the specific kind of combination you want, whether it's sort of closer to the experimental data and analyses or closer to the theoretical side. But an important thing is it's some kind of combination, and you sort of figure out where you want to be in that combination. So that's it in a nutshell, if I kind of answered the question.
Perfect. So I guess, so Nancy, I'll sort of turn the floor over to you now. I've invited Sue Ann up on screen so she can put her 2 cents in as well.
So I think there are 2 aspects to this. First is figuring out what it is you want to do, which is not easy. And that is one of the roles of your thesis advisor and anybody else that you can get to mentor you, is to lay out what are the things that you like and what are the things that you don't like, and what are the options for sometimes the options are things that involve, sometimes the options are reduced by family-related issues or health-related issues, and just kind of coming up with what is it you want to do. It's important. Then you have to figure out how to make that happen. And there it's important to start contacting as early as possible people who you might want to work with, and let them know what your background is and what it is exactly about what they're doing that you want to help with. Because generally, people who are taking on postdocs are looking for people to do semi-specific things, and they're looking for people whose backgrounds match their things. And once again, there's a place where the thesis advisor can help you make those connections. But it's a very active process.
Fantastic. So, Sue Ann, you obviously are in a little bit of a different setting where you're still in the math department. You're more of an applied mathematician. I always say there's a scale in computational neuroscientist, not science, between the math and the biology. Yeah. And you're much more on the math side of things. Yeah. I wasn't going to go that far, but you did for me. So yeah.
Okay.
So I guess, have you found any unique challenges being there and sort of trying to motivate your very mathematical work for the neuroscience community, and perhaps vice versa?
Yeah, I think so. So one thing I would say, I'm very lucky that I'm in an applied math department. So I have colleagues who are basically physicists. I have colleagues who do geophysical fluid dynamics. So that it can be harder if you're in a straight-on math department, depending on. So that's sort of motivating the applications to your colleagues, right? So I think, yeah, so there's that aspect. And then, yeah, I do struggle. I like to collaborate with what I call real neuroscientists, like Francis. Collaborated with, because I feel like then they can, for one thing, keep me grounded into what are important questions to think about, and also, yeah, help with that, motivating the, kind of making that connection. So yeah, I think collaboration is really important. In my work, I tend to have a spectrum of problems. Some are much more mathematical, and then I do more applied stuff, and that tends to be in collaboration with either biologists or neuroscientists or that kind of thing. But it is a bit of a struggle. Also, it's a struggle in a math department to recruit students.
Mm-hmm.
In a while to get to the point where you're you can find the students that want to do that kind of work, that are interested in the applications, right? And what's been really helpful is we at our university started a Center for Theoretical Neuroscience. Although we don't do a lot, it's a name. And
Right.
Oops.
but having that center has really helped students find me that are the right fit, right? And postdocs and things like that. Yeah.
Yeah, so I'll quickly say from my personal experience, when I got my degree from University of Michigan, there was a applied and interdisciplinary mathematics program that, you know, I applied to that as opposed to pure mathematics. Hi, John. But so I think that's something that's very helpful. And if you're an undergraduate student that wants to pursue, you know, this graduate degrees, that might be something to look for. And it's hard to find. Not all places have that, but any place that, you know, has something that says, you know, applied mathematics is, you know, you're probably more likely to find that some of that interdisciplinary, some of that collaborative opportunities I think we all agree is necessary for computational neuroscience. So we do have a couple of questions from the audience. So I'll go to this one first, which is probably the least fun one, but we'll get it out of the way. So Emily was asking sort of broadly about how you guys think that COVID-19 is going to affect recruiting and job searching, and how you think, you know, potential new graduates, postdocs, et cetera, should potentially adjust their plans in the near future. Who wants to go with that deep question?
Go ahead,
I'll
Nancy.
start and say that we're reasonably lucky compared to the rest of academia because we can do most of our stuff online. And the interaction between a mentor and a mentee can be done on Zoom. It's not the same as in person, but you can keep going if you don't have to use a lab. So I think that my understanding is that all universities are trying to keep their research going in one way or another. And that means that people will be trying to recruit people to do the work. So I'm not sure that for recruiting, it's really going to be that different than we had before, except that we may not require that people come to the cities in which we live.
Yeah. I mean, I would second what Nancy just said, is that, you know, us who are doing sort of dry computational work are very fortunate. The challenge, so once the work is ongoing, like you can kind of continue with a, you know, a few blips. But I think if you're going to hire someone as a student or postdoc, it's sort of important to sort of have the initial in-person interaction. And so that's what I think would be affected. So, you know, you could do like Zoom helps a lot because you can have the face-to-face interaction. So I think that does mitigate it to a certain extent. But I guess the change is that if this sort of virtual goes on too long, it might delay in terms of, you know, making a final decision about recruitment. But if it's ongoing, I think, you know, it can continue. That's my take on it. Yeah. So that answers the question. Yeah, go ahead, Sunan.
I was going to say the only thing I would add is some universities are certainly feeling a financial crunch because of various issues, whether it's student enrollment or, you know, the stock market crash effect on their endowment. But so that, from my perspective, I certainly am seeing things like, you know, people's individual research grants are still there, and if they have money, they can hire people. But if you're looking at students that are partially funded by teaching assistantships or by university money, like we have a departmental postdoc program, I'm expecting that'll probably be canceled next year because we've been given a big budget cut. So there may be issues like that, right? Like people who have ongoing funding, it's great. You still have your funding, you can keep using it, but institutionally sponsored things might just affect the availability of certain things. We're worried about how many TAs we'll have in the fall because we're worried about how many undergrads we're going to have. And if we don't have a lot of undergrads, we don't have a lot of TAs, it's harder to get more grad students, right? Yeah.
Right.
Interesting. Well, thank you guys for speaking so honestly about that. I think
that's not even needed, but I think in terms of the interaction side of things.
Yeah, no, that's something that I think I'm sure a bunch of people here are anxious about. So thank you guys for being so open with that. So a couple more fun scientific questions now to talk about. So this one's primarily for you, Nancy. You showed results from your modeling, and people are wondering what would be the experimental protocol that you'd like to see to sort of test the mechanisms that you've been proposing.
Yes. Well, I have a lot of interactions with experimentalists now, and things are really happening. One is a grant I'm just about to re-put in with people who are working on fear conditioning in zebrafish. And in that case, the model is suggesting which particular rhythms are associated with which particular interneurons, which interneurons are associated with feeling safe or feeling not safe. There are a lot of very, very specific situations. And in that case, they have a lot of tools because larval zebrafish can be are transparent. You can see the whole braining. You can see how in training the different networks build up. So that's one thing. I have another collaboration on Parkinson's disease in which we're trying to understand how it is that using march music allows people with Parkinson's to start moving. And we think it has to do with the fact that the march music is breaking up the beta. So our networks, our research about where the beta comes from and how it can be broken up so that other things can happen, instead of just doing the status quo of staying there, is a really important question. And we've found a Parkinson's degree surgeon who will do this at the soonest possible opportunity.
Interesting.
So that's another. I have one that's about the notion of attention. And here it's working with monkeys. And we're looking at the rhythms in 3 or 4 different things. And the model is making a case for how rhythms allow changes of attention, allow things to happen between taking things in and acting on them, which is similar to what was talked about before about retrieval and encoding. But this isn't just retrieval and encoding, it's more, what do you do with the information that you have? And so we are able to take the data that people have, turn it into models, and have those models be very specific about what should be seen. So I can't answer this in general. It's more that every good model suggests good experiments, and then you do them.
Yeah.
Fantastic.
Yeah, I completely agree. Scott, can I say one thing that I think speaks to other things that are brought up? So, I think what, especially like speaking to sort of the trainees out there, is like, I sort of have 3 points here that I wrote down. Sort of terminology kind of issues when it's interdisciplinary that Scott spoke to very, very nicely in the sort of the beginning. 2 is sort of the experimental data and kind of what experimental data you're referring to, sort of like in the different scales I was talking about. And 3, what sort of essentially are the goals of the modeling that you're doing. And so the first thing I like to mention is something that Nancy wrote, I forget how many years ago, but it was in regards to a detailed model that Roger Traub put together of the, the different layers. And the question is, when do we sort of start using these models to come up with ideas. And forgive me if I sort of say it wrong, Nancy, but really what I took from that is like, it's not about the mathematical model saying, okay, this is the model and this is how the system works. It's about creating the ideas and sort of, the hypothesis being developed. So for example, Nancy, what she spoke about today and sort of including the biophysics have been important, but they're sort of, simpler models compared to sort of detailed multi-compartment model that we might do. So it's a different kind of thing you're going to get out of it. But as she said, something might be wrong, but it's not crazy. And it generates ideas that then you can interact with the experimenters or should we do the experiment this way, something you hadn't thought about, right? So I think it's important to sort of distinguish between these sort of aspects because experimental people tend to think of a very detailed thing and a model may not be representing it quite in that way, but at least it's generating the ideas of how to start thinking about, have those conversations, like all the collaborations that Nancy was talking about. So that's really what's important, which I think sometimes gets lost in the different types of models of going back. So that's sort of it in a nutshell that I just wanted to comment on.
Thank you, Francis. So looks like we have 2 more questions. And again, if anyone has any questions, no limitations on topics, anything you want, feel free to post them. So there's one that was a little more technical that I'm curious what people's thoughts are on. So this Dean had said that when he had been modeling spiking networks, he had been using more homogeneous point neuron models with either Poisson noise or background Poisson inputs. But following the talks, he's starting to feel it's important to use oscillatory noise for background inputs. So how and when should a model use these sort of oscillatory noise, oscillatory background input, or when is it appropriate to perhaps use something slightly simpler? I'll sort of leave that open to whoever wants to grab it.
I mean, I would just say initial thing, it kind of just depends on what the question of the model of what you're doing, right? There's not a generic answer. It depends on the details of context.
Yeah.
Once you know, then there's sort of technicalities of what is the best, Brian, to...
And what kind of question you're trying to answer, right? Like your model is usually motivated by some question that you want to investigate, right? So what's important to that? Yeah.
Yeah, and I think that sort of goes to what I've learned, especially working with you, Francis, which is there never is any be all, answer that applies to everything. It's always the answer is always specific to the situation. So I think, with something like that, it very much depends on how detailed of a model you're looking at for how detailed of the, answers you're trying to get. So another question that this one is a little bit more general. Is from Dimitri, who said that different oscillation modelers have very different approaches and levels of detail when they're constraining their models to the data. Is there a more or less well-defined criteria that allows you to distinguish between sort of spherical cow-like research and something more biologically focused?
No.
Yes, that was my. I think.
I don't want to take over from Nancy and Sue-Ann, but yeah.
I would say if you're using a spherical model, your challenge is to show that it's relevant to what you're talking about. If you're using a kitchen sink model, your challenge is to show that most of the details that you're putting in are in fact relevant. Everybody who does modeling has to justify the details that they're using and tie it to the particular answers that they want to get out of the model.
Yeah. Mm-hmm. Mm-hmm.
Yeah, I agree.
Yeah.
Awesome. Yeah, no, I think that's a sort of theme to a lot of these questions here, which is, unfortunately there's not always a clear answer. That definitely depends on what your specific topic is and what type of conclusions you're trying to draw, which is part of what makes our field a little bit more challenging.
And actually to that, I would add one small thing is that, as we move like with sort of the publishing world and stuff like that, there really should be more emphasis put on sort of the methods and the rationale when you have the models. Because here's this model, I use it to explore this, and I use 0.1 millisiemens per square centimeter. I mean, there was a reason people made certain choices. So there's a reason Nancy's using, focusing on M channels, right? And so Nancy might explain it and sort of, present the ideas of where it comes from. but there's a lot of papers that don't. So when somebody's reading those papers, they don't know, okay, well, why did you do that? So why did you make that choice? So you really need, if you read a paper and it doesn't explain why they made a certain choice, I mean, I would just sort of ask them. And if they don't really have a clear answer, then, you take it with a grain of salt. But it's also okay to say, I use that because it was easier to analyze the data. I use an integrated FHIR model because I can actually do the theoretical analysis and get some insight, and then sort of link it to something else. So the main thing is actually,
but that's, I really dislike that answer. I mean, I think integrated FHIR models are very useful.
Yes.
But you have to say that it's useful in this context, not in another context.
Yeah.
You have to say that for the questions you're asking, you're not leading the essential issues. And for a lot of the questions I ask, all of those other currents, like M currents and D currents and A currents and blah, 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 are actually the essence of what is producing the rhythm, and therefore how the target is reacting to its input. So you leave that out, you put in integrated FHIR, and you've left out everything that is relevant to what you're talking about. Whereas if you're just talking about gamma, integrated FHIR works really well.
Yeah.
Because it doesn't have all those crazy other currents in it.
Mm-hmm. Yeah. And I think this is where sort of the balance becomes in terms of what kind of experimental data you're accessing to constrain whatever's in your model starts getting sort of finicky. Because, I mean, as you know, I completely agree with the whole biophysical notion. We need that. But then once we make certain choices for the biophysics, the time constant that you're using for the parameter set, that sort of dictates certain things. So it's important to sort of be clear also, too, if you have the multi-compartment, so I clearly agree that the integrated FHIR, whether you have biophysics or not in your cellular model, that's a world of difference. But then once you make that choice, then there's this other world of difference to come in. The integrated FHIR and simpler models, of course, are extremely helpful when you have these sort of large systems, right? But then clearly they can't say anything about, the biophysical, but, and they may be totally irrelevant, but that could be also true on the other end. So I think it's this kind of balance and the struggle that we all as modelers sort of deal with. And so, the important thing is that we're dealing with some kind of experimental data or experimental dispersion, and the model is actually giving us some insight and understanding in some way. That's kind of how I view it.
Yeah, I would add sometimes it's useful to look at more than one type of model, right? I think even in Frances's talk, she did that, right? You can look at if the simpler model is easier to do more in-depth analysis or even just running more simulations, but then having that check with a more detailed model, that it is useful, right? Can be helpful. So sometimes you can balance it off that way, if that's appropriate.
Mm-hmm.
Awesome. So we'll do one last question here, which I think is, this is a good question to sort of end this session. Thank you guys so much for agreeing to do this and giving such great answers to these questions. So Sahel asked very generally, what first steps do you suggest for an undergraduate student to get started in computational neuroscience research? That's a big one.
I mean, if you're at a university where you have an opportunity to work with contact a professor and work with them either on a short-term or a long-term research project, that's a great starting point, right? It might even be a project in a course, right? Or it might be a summer research term, or, there's lots of, but a starting point is like talking to a professor that works in that area. And, I know some places people volunteer in labs, right? Well, I don't have test tubes for you to wash, but I might have simulations for you to run. So, there's. I think that's a good starting point to get a sense of what people are doing.
Yeah. I mean, I guess the only thing I would add for the undergraduate level is, at the undergraduate level, make sure you get your sort of like basic foundation of differential equations, linear algebra, and things like that. And try not to like just kind of go all over the place. I get sort of those basics understood, right? So because when at the graduate level, if someone doesn't know what a differential equation, they might know everything about neuroscience and the brain, but if you don't know the fundamentals, it's hard to kind of get started. So I think you want to try and make sure most of your undergraduate is getting sort of solid foundations in the mathematical model, mathematics is how I would put it. I mean, I didn't know about stuff. So, I mean, my undergraduate was applied math, and I was always interested in biology. But if I didn't sort of have that appreciation of, nonlinear systems or linear algebra, like it would have been hard to kind of appreciate certain things, is how I would put it. And then, people go into directions, right? And, what aspect. But having that foundation allows you to kind of move forward. That's at the undergraduate level. That would be my suggestion.
On the other hand, it's really also important to have some background in biology.
Yep.
So you need some courses in biology to give you a sense of the squishiness. I love that word. It's the fact that things that are pretty black and white in mathematics are all over the place in biology.
Yeah.
And learning to be able to create questions that are associated with biology.
Yeah.
So in many cases, they'll tell you things, I did this, I did this, I did that, and this follows from it. But there's no reasoning about how this follows from it. So you can learn to read between the lines and see what's actually there and what actually isn't. And that's by having both the math and the biology, you have the training for asking questions and the material about which to ask those questions.
Yeah, I guess I'll just quickly add on that front that a lot of it comes about, reaching out and sort of, knowing as many people as you can to sort of find these opportunities. When I was an undergraduate, I was a math major and I was also pursuing pre-medicine, and I had no idea which one of those I wanted to do until quite literally the summer before my senior year. And I was doing a summer research program, and I just sort of happened to meet a professor who did a computational neuroscience research. And once I sort of knew that was not, an avenue, the rest was history. So I think, I lucked out a little bit and, getting the good luck of meeting that professor and finding that avenue. But I think that just goes to show that if this is something that you are interested in, it's what you want to do, you may have to be a little aggressive in looking for and finding and pursuing those opportunities. But once you do, then, there's so many cool things to do in this field. So I think that sort of ends our time here.
More time? Okay.
Yeah. Francis, you want to add on?
Yeah, I kind of wanted to make a comment and sort of ask Nancy at the same time, is that while I completely agree with you about the biology part, I think, unless there's a sort of a fundamental interest in the biological system,
I agree on that too.
Yeah, because I
agree that you need that basic mathematical background.
Yeah. But I also think that, if you don't have the biological side in the undergraduate, it's sort of less critical. But, I think you're either interested in the biology or not. So like Scott was interested in medicine. And so for the trainees out there, if you don't, it's really like, oh, this is cool stuff to do mathematically, then, it's sort of different. That's all. I'll stop there because there's other things there.
Yeah. Okay. Awesome. So I think this was a great discussion. Thank you all so much for agreeing to participate. For everyone who is out there watching, we now have our lunch break. So our next session begins at 2:00, where John is going to take over and give a tutorial on some ideas underlying macro level brain oscillations. So thank you guys for a great first session here, and we will see you all again at 2:00.
Okay. Bye. See you soon. See you, Scott.
Bye.
Bye.
Thanks.